And I'm going to, by default, mute everybody. So remember, if you have a question, just unmute yourself and shout it out. Okay, so what had we done last time? Just to review, we'd introduced the concept of a basis. And so a basis is a set of vectors or kets. Ket is a synonym for vector, which are linearly independent. Okay, and there's some label that this is J. J is from 1 up to the dimension of the vector space. Actually, to save bandwidth, I'm going to stop my video here. Okay, and so if you have a basis, then you can take any ket. Let's take a generic ket V and write it as a linear combination of the basis elements. A sum from J is 1 up to the dimension of some numbers little v sub j times the basis elements, phi sub j. And the v sub j, we decided were called the components of the ket V. Now, one thing that could happen is that instead of the label being a bunch of integers from 1 to n, maybe the label is continuous. So what if label is continuous? And so there are lots of examples of this that we will run into. One example could be, for example, the label is the position of a particle. It could also be, for example, the momentum of a particle or the angular momentum of a particle, although that would not be continuous, it turns out. Okay, so what if that happens? Then your basis instead will look something like this. It's still a set of kets, but I'm labeling them by alpha. And A is less than alpha is less than B, perhaps. That means we've localized our particle between A and B. But alpha here is, instead of being an integer, a continuous real number. Okay, then the way we would write our component equation is we'd say our ket V, instead of being a sum, is going to be an integral from A to B with respect to the label alpha of some numbers V of alpha times our basis kets, phi alpha. So again, V of alpha are known as the components. But in this case, they're functions of alpha. And in the case where alpha represents x, let's say, the position of a particle, this is the wave function, about which we will have much more to say later, of course. Okay, so that's an aside. For today, we're not going to talk very much about continuous labels, but that's how you would do it if you had to. The other thing we did last time is we introduced the concept of an inner product of two kets. Let's call them V and W. And then that's a complex number in general. Could be real. But it obeys the following rules. Rule 1 was, if you take V with W, that's the complex conjugate of W with V. The star here, the asterisk, means complex conjugate. From that, as we mentioned at the end of last time, it follows that the inner product of any ket with itself is positive and real, or maybe I should say real and positive. unless V is the null ket. Okay, and so now we can make some definitions. So our first definition is having to do with orthogonality or perpendicular vectors. So V and W are orthogonal or perpendicular if they have zero inner product. And if they have zero inner product, of course, it doesn't matter whether we write VW or WV because of the rule up here about complex conjugating. If it's zero, it's zero. Okay, so that's orthogonal or perpendicular. Another definition we'll need is that of the norm. The norm of a ket or vector V is given by the square root of its inner product with itself. So if it's not null, that's a positive number, so it's nice we can take the square root if we want. And if it's not null, then this is a non-zero number. So if not null, then we can form this ket. We take the original ket and we divide it by its norm. And then you can check from the definitions that we've already made that this has norm 1. Okay, so given any ket, you can always take a ket and form a norm 1 ket out of it. And one of the principles of quantum mechanics is going to be that it doesn't matter what the norm of a ket is as long as it's non-zero. And so there's a nice way of deciding a standard way of presenting the ket, and that is to choose it to have norm 1. But if I hand you a ket, it may or may not have norm 1. You have to check. And if it's not, you may have to put it in this form by dividing by the norm. Okay, that gives rise to the concept of an orthonormal basis. I misspelled it, of course. Orthonormal basis has 6 syllables and too many letters. And so from now on, I'm going to just call it an orthobasis. This is not, I think, very standard language. This is my own private thing that I invented for this course, but that's okay. So an orthobasis is the same thing as an orthonormal basis, and it's a basis set of kets, phi sub j, that satisfies that if I take the inner product of any two of them, I get either 0 or 1, depending on whether they're the same thing. So I write that as delta jk. That's the Kronecker delta, which is 1 if j equals k, and it's 0 if j is not equal to k. Okay, so given the fact that we can always, it turns out we can always take an ordinary basis and turn it into an orthobasis, and we'll explain how to do that in a little bit. And you also get to do some of that for homework. Okay, but first let me make one more definition, and that is of a dual vector space. Okay, the dual vector space is composed of objects like this. We have a left angle bracket, V, and then a vertical line. This is a map from the kets into the complex numbers. And so you could ask, well, what complex number do you get from this map? And the answer is the inner product. So specifically, the complex number that you get is the inner product. Okay, so if I have a member of the dual vector space that I call V, and I act with it on a member of the ordinary vector space that I'm going to call W, that just means that in the end, I get the inner product V with W. That's what those words mean. And so if you think about it, that means that putting the parentheses here on the left was really kind of a waste of time, and so we just won't do it anymore. We will just write this when we mean that. They mean exactly the same thing anyway, and so that's just a waste of time to write the parentheses. Okay?
Professor?
Yes, go ahead.
I'm sorry, could you please explain very briefly again, what do you mean by map from the kets?
It just says that if I give you V and I give you any ket, it's going to give you a complex number, right? So it's just saying, given a ket, I act with V and I get a complex number out. Okay, and then this was telling you what complex number you get out. You get out the complex number, which is the inner product of V with W. So in a way, we haven't really done anything there. We've just said that we're going to regard this dual vector V as being the thing which, when acting on another vector W, gives you back the inner product of the two. Okay?
Mm-hmm. Thank you.
Sure.
That makes sense. Would it make sense to talk about these in terms of like calling them a function that acts on the kets? Or is it just
yeah, it's very similar to a function. I think a mathematician would probably object to that, but you can think of it as a function if you want, because this isn't a math class and we don't care about technical details. But a function is a map from, say, a real number to the real numbers, or a complex number to the complex numbers. This is a map from the kets into complex numbers. That's specifically what kind of a map it is. Okay?
Gotcha, makes sense.
Okay, good. And so, by the way, these are given a name of bra as opposed to ket. And so it's sort of a joke, because then the bracket is the bra combined with the ket, like we've written there. Okay, so I'm not going to prove it, but it's actually, I think, not too hard to prove, if we really wanted to, that the dual vector space is also a vector space. In fact, it's a vector space with an inner product. And so if we wanted to, we could define everything in terms of the bras, introduce an inner product from them, and then say that kets were the map from the bras into the complex numbers. But in the end, it all just boils down to knowing what is the inner product. And if you know the inner product, then you know what these two maps are. And so really that's all there is to it. Okay. So another way of saying that is this, that the inner product is a map from the kets and the bras into the complex numbers. So that's saying, given a ket and given a bra, the inner product tells you a complex number. You can also think of it as just given two kets, you get a complex number, or get two bras, you get a complex number. And the reason those are all the same thing is just because of the way that the dual vector space is defined right here. Okay. All right, so let's say I'm given two vectors. let me call them V and
I'm sorry,
W.
Professor.
Yes, go ahead.
You mentioned inner product is a map from ket raw. Does that mean you're reversing it? Or
So it's really, in a sense, all the same map. It's just that because given a ket, I can make a bra out of it. Given a bra, I can make a ket out of it. I can talk about it as a map from kets and bras to the complex numbers, or two kets to the complex numbers, or two bras to the complex numbers. But the complex number you get out in the end is always just the same thing. So it's really just sort of introducing some language to describe that fact, that given a ket, you know what the bra is and vice versa.
okay, thank you.
Okay. All right. So given a vector or a ket, from what we said earlier, we can write it as a bunch of components times a bunch of basis vectors, phi sub j. And we can do the same thing with some other vector. Okay, and a reminder that defines the components. And now suppose I take the inner product of these two. So I write that as V inner product W. And what's it going to be? It's going to be a sum over all j and all k of V sub j complex conjugate Wk of phi j phi k, which is equal to a sum of just over j of V sub j star W sub j. Now, why is that? That's because this thing, if it's an orthobasis, I should say, if, that's very important, we're talking about an orthobasis, not just an ordinary basis. And the reason for that is phi sub k is mostly zeros unless j equals k. So only the j equals k term in the double sum here survives. And so really I've just got a single sum over all the j's. And then I can set this w sub k equal to w sub j. And so that's how I get this single sum here for the inner product. So all this is saying is if I know the components, then I know the inner product of two vectors in terms of the components. So one way of thinking about this is to think of your ket W as being composed of column vectors, or this one's a single one, so it's a single column vector with components W1 up to W sub n, where n is the dimension of the vector space. And think of your bra, in this case V, is a row vector. And so I would write that as V sub 1 complex conjugate, V sub 2 complex conjugate up to however many there are, V sub n complex conjugate. So notice that when you take the bra, the rule is you complex conjugate the component. Okay, then our formula up here for what the inner product is going to turn into VW is just V1 star, V2 star, up to V sub n star. We just do the usual sort of matrix multiplication of two vectors with a row vector times a column vector. And so the important thing is just, so this is the, oops, that didn't work. This right here is the same thing, but it's just written in non-ket language. And so this is often called the matrix representation for what we're doing, namely taking the inner product. So far, they're just vectors, but we will introduce matrices when we start talking about operators. Okay, so now I mentioned earlier that given an ordinary basis, you can always construct an orthobasis, and there's a theorem to that effect. The theorem, when you prove it, the proof is more important almost than the theorem itself. So this is the Gram-Schmidt theorem and process. Okay, and so here's the statement of it. Let's say I'm given an ordinary basis, which I'm going to call, for the purposes of this theorem, psi sub j. So these are linearly independent, but they're not necessarily orthonormal. Independent, I can't spell today. But given them, you can construct an orthobasis. And so to prove this theorem, all we're going to do is go through what that process is. You do it by taking linear combinations. And one of the statements about what makes a complex linear vector space is you can take linear combinations and be sure that your linear combinations will again be within the vector space. Okay, oh, and let's call our orthobasis, just to distinguish it from the original basis, let's call those, oops, I don't know what that was. Let's call those phi sub j. Okay, so we need to construct the phi sub j's out of the psi sub j's. Here's step one. So step one is you just choose any one of the original kets. Doesn't matter which one. Choose any ket in the original basis. And so we'll just choose the first one. Why not? So we'll choose psi sub 1. Of course, you can relabel them to make it any one you want. For convenience, it might be better to choose something, a different one. Okay, and then you divide by its length, otherwise known as its norm. Okay, and so that's psi 1 divided by the square root of the inner product of psi 1 with itself. And that's going to be the first of our orthonormal basis kets, or orthobasis kets. Okay, so we're going to call that phi sub 1. So the first step is easy. There's almost nothing to it. Step 2 is you choose a second ket from your original list. And let's call that psi 2. We assume that they were originally arranged in that order. And so the idea is now what we're going to do is subtract off the projection along phi 1. So what do those words mean? We're going to define a new ket that I'm going to call psi 2 twiddle. Psi 2 twiddle is defined to be psi 2 minus, and this is the projection part, phi 1 times the inner product of phi 1 with the original psi 2. So why would we do that? The point is that this psi twiddle 2 is automatically going to be orthogonal to phi 1. Okay, and so the proof is if you just take the inner product of phi 1 with this up here, you'll find out that because phi 1 has norm 1, we just get phi 1 psi 2 from here, from taking the inner product with that, minus phi 1 from taking the inner product with that, which is 1, times phi 1 psi 2. So in the end, we're going to get 0. And so psi twiddle 2 is orthogonal to phi sub 1. So the only thing left to do is to divide by its length.
Professor?
Yes.
Sorry. So I was actually wondering, what exactly does it mean mathematically to have a ket before an inner product?
So if you want, you can do all of this stuff without ever defining an inner product. It's just that it wouldn't be very useful. You wouldn't be able to do any physics with it in particular. So it would be like having a vector space where you've never, a set of vectors where you've never defined what it means to have the length of a vector. You should think of the norm as sort of the length of the vector. And so if you want, you could talk about vectors without ever talking about their lengths, but that wouldn't be very interesting or useful, right? And so in particular, to define how quantum mechanics works, we're gonna definitely need the inner product. Does that answer your question?
Kind of. I'm just like, wondering what mathematically taking a ket and multiplying it by an inner product looks like and what it means per se.
You mean taking the inner product with another vector? Is that what you mean?
The inner product itself is just a complex number, so it's either real or it just has like an I with it. So you're just multiplying the ket by a constant.
So yeah, so there's two things you can do. You can multiply a ket by a constant, any complex number you want, or you can take its inner product with another vector. So you should think of multiplying by a constant as like scaling the vector, scaling the ket, making it larger or smaller. But the inner product is like the dot product of two vectors. And so when you take the inner product of a ket with itself, that's like deciding what its length is, right? So you can always scale a vector without ever talking about its length. That's multiplying by a constant. But the inner product is what's actually telling you how long the vector is or what its size is.
Okay.
Okay?
Okay.
All right, good.
Can you repeat that last part one more time? What defines how long and what size it is? The inner product?
The inner product does. And specifically, if you've got a ket, you take its inner product with itself, take the square root. That's actually this denominator here. And that's the norm as we defined it. The norm of the vector you should think of as its length. We could use the word length, but it's just more traditional to call it the norm. Okay.
So in this psi 2 that you defined in step 2, by the inner product, does that mean we're projecting phi 1 onto psi 2 and then multiplying it by the length of phi 1 with that? So is that what we're doing?
Yeah, so you should think of this as telling you how much of psi 2 is along the direction of phi 1. That's a number. It's the projection of psi 2 onto phi 1. And then you're multiplying back by just the phi 1 part here. And so think of it in terms of ordinary vectors. Suppose I had an ordinary vector in the xy plane. I could think of as phi 1 as just the unit vector along the x direction. And so this part would be telling me what's the x component of psi2. That's just some number. And then I subtract off that number times the unit vector along x1. And so what I've got left, the whole thing, is going to be a vector that's got no x component to it.
Will you set an example of this as well?
Well, you'll get to do it for homework. So if you follow the recipe that I'm in the process of doing here, you'll see how it works. Maybe I'll do an example. Yeah.
Thank you.
Yeah. Okay.
Thank you.
Good. All right. So just to continue where we were, we made this psi tilde 2, and the way we constructed it makes it orthogonal to phi 1. And so now we divide by its length, or its norm. And that's going to be our second orthobasis component. Phi 2 is defined to be the psi tilde 2 divided by its norm, which is the square root of its inner product with itself. Okay, and as I mentioned earlier, that means phi 2 automatically has norm 1. Okay, so this has norm 1. And it's orthogonal to phi 1. And so far now I have two vectors that are orthonormal. Okay, so now we're just going to repeat. It's probably easier to do this if we write down the general step, which I will in a minute. So choose a third ket from our original list, which we're going to call psi 3. Now what we're going to do is subtract off from it the projections along both phi 1 and phi 2. Okay, so those are just words. What do we actually mean by that? We mean that we're going to define psi tilde 3, which is going to be the original psi 3. And now we subtract off the following things. Phi 1 times the inner product of phi 1 with psi 3 minus phi 2 with the inner product of phi 2 with psi 3. Okay, and the strategy here is that what we've done is we've made a ket that is orthogonal to all of the orthonormal basis vectors that we've got so far. Namely, it's orthogonal to phi 1 and to phi 2. And to prove that, you can just take its inner product with phi 1 and see that it's 0, and then with phi 2 and see that it's 0. The only problem with this thing is it doesn't have norm 1. So that's the next step. You divide by its length, or its norm. I'm going to write length equals norm. You should think of them as synonyms to get our third member of the orthobasis. Phi 3 is just psi tilde 3. The only thing that was wrong with this, it didn't have the right length. So we divide by its length. And this has norm 1. So it has norm 1. It's orthogonal to phi 1 and phi 2. The way we constructed phi 2, it was already orthogonal to phi 1 and had unit length. And so that's the idea. You just keep doing this. Let me write down the general step. So this is step n, little n. So step little n is you take the nth vector of your original basis and you define its twiddle. or it's tilde, by you take it and you subtract off its projections along all the previous orthonormal basis vectors that you've constructed. So that means you're going to subtract off the sum from j equals 1 up to n minus 1, because you've constructed n minus 1 such vectors, of phi sub n, or sorry, that should be phi sub j. Let me erase that. This should be phi sub j onto psi sub n. Okay, so note psi tilde n is orthogonal to all the previous orthonormal basis vectors, all the previous phi sub k's, for k equals 1 up to n minus 1. Okay, and let's just check that. Let's just write out why that's true. Suppose I take the inner product of phi sub k with psi tilde n. Okay, so there's one term from here, which is inner product phi sub k with psi sub n. And then there's this term from the sum here, which is going to be a sum from j equals 1 up to n minus 1, inner product phi sub k. I have a bad habit of mixing up my phi's. There's two different phi's, and I'm using them interchangeably. So it's phi sub k, phi sub j, then the inner product phi sub j with psi sub n. Okay, so this just came from that. Okay, and this just came from here when I took the inner product with phi sub k. Okay?
Professor?
Yes.
I got a question.
Yes.
Look, if the psi of n is orthogonal to all of these phi's,
Yeah.
wouldn't the projection be 0?
No. So that, well, the inner product with them is 0. That's what I'm in the process of proving right now. So it's the fact that you've subtracted off its projection onto all these other vectors means that its inner product with any one of them is 0. Okay, and that's exactly what we're in the process of doing right here. Okay, so that's what I did. I wrote down the inner product here, and it's got two parts. It's got this part, and it's got these parts. And now the key thing is, because the phi k and phi j that we'd already written down were orthonormal, this is equal to the Kronecker delta of k and j. In other words, that's saying it's 0 and doesn't contribute at all except when k equals j, and when k equals j, it's just 1. And that means there's only one term in this whole sum that survives, and that's the term when j is equal to k. And so I might as well set this equal to phi sub k, psi sub n. That's the only term that survives. And so this is phi sub k, psi sub n, minus phi sub k, psi sub n, which is 0. Okay, so your intuition is correct. When I take the inner product of psi tilde n with any one of the previous phi sub k's, it's 0. That's showing that it's orthogonal. The other part of an orthonormal basis is I need this thing to have norm 1. It won't necessarily have norm 1, but I can cure that just by dividing by its norm. Okay, and so now we define.
I'm sorry, Professor.
Yes?
I still have another question. So you mentioned psi of n is orthogonal to all of phi of k for k equals 1 through n minus 1.
Yes.
So doesn't this mean that all of these phi of k's are in the same plane? And in other words, they should be in the same basis?
No, so they are all orthogonal to each other. So if you have a three-dimensional vector space, then you should think of these as being like the unit vectors along x, y, and z.
Mm.
But in general, our vector space might have many more dimensions than that. And so you can't think of them as being in the same plane because the vector space has many more dimensions than 2 in general.
So how would you define orthogonal in that situation when it's not three-dimensional?
Oh, you just look at the inner product, and if the inner product is 0, then they're orthogonal. If the inner product is not 0, then they're not orthogonal.
Okay, thank you.
Okay. All right, so now we define phi sub n to be this psi tilde n. The only thing that was wrong with it is it didn't have the right length or norm, and so we just divide by its norm. Okay, and this has norm 1. Okay, and so now it joins all the other phi sub k's, and you just repeat. And you do step n, where n is the last dimension of the vector space, and then you're done. So for homework, you're going to get to do 2 examples of this, one with dimension 3 and another with dimension 2. Okay, so we won't, but you can set up a computer program to do this for any dimension you want. All right. Good. So it's actually, I think you'll learn more about how this works if you just do an example. So let's do an expansion. Oops. Let's do an expansion of a general vector in an orthobasis and see how that works. Okay, so if I write my v, my vector v, as a sum over components in my orthobasis, I can ask, what are the components? And fortunately, there's a very nice way of answering that question. And the trick is you take the inner product with some other member of your orthobasis, a generic member of your orthobasis. So take inner product with phi sub k. I'm writing it in the bra form. And so what we get is phi sub k inner product with v is equal to a sum over j, v sub j, phi k inner product with phi j. But we're going to do what we usually do whenever we see an inner product of orthobasis elements. That's equal to the Kronecker delta. It's 1 if and only if j and k are equal, otherwise it's 0. And so only one term in the sum survives, and that's the one where j is equal to k. And so the answer for this is just v sub k. Okay, so what we've learned is that we know what the components are. V sub k is in fact the inner product of phi sub k with v. So that only works if you have an orthobasis. That's one of the reasons orthobases are valuable and why we have this Gram-Schmidt process. If I just hand you a basis, it may or may not be an orthobasis. You might have to construct the orthobasis by going through the Gram-Schmidt process. In any case, if we've done this, then we can rewrite our vector v in the following way. that V is equal to sum over J, phi sub J, phi sub J, V. So all I've done there is these are my components. These are my orthobasis vectors. And so I've just rewritten this equation, but in a way where the components don't actually appear because, well, they're here, but I haven't written them as V sub J. Okay. So that's going to be a very useful equation, actually. We'll see why that's so useful later. All right, it's time to now move on, though, and talk about linear operators. So linear operators are things that map kets onto kets. In other words, they take a ket and they give you a rule for getting another ket. So if I act on, let me call my operator A. If it acts on a vector V, that's a ket. What ket is it? We call the ket A times V, or A acting on V. And also, it turns bras into bras. Excuse me. So if I have a bra V acting with A, that's a bra. And it has to have some properties of linearity. So the properties that it satisfies are, if I act with A on some linear combination of vectors, it's the same thing as, my coefficients are B and C here, it's the same thing as B times A acting on V plus C times A acting on W. In other words, you can just move the coefficients, the complex numbers, wherever you want with impunity. And similarly for bras.
Professor?
Mm-hmm.
Just wondering, this may just be, a technicality, but when you say mapping a ket onto a ket, as opposed to mapping a bra into a bra, is there a mathematical difference between the two?
Not at all. That was just
okay.
me being sloppy.
Okay. All right. Thank you.
Yeah, I'm not super mathematically precise in this class. Okay, so let's give some examples. The first example is the easiest, and that's there's something called the identity operator, which basically does nothing. We're going to call it I in this class, and it satisfies that if I act with I on any vector, I just get back the original vector. And if I act on any bra vector with I get back the same bra vector. And it's important that that's true for every vector. Okay, so that one's too easy. Let's just do one more before we stop today, and that's the projection operator. Onto a state or onto a vector. Okay, and the way that's defined is P sub x, that's the name of my projection operator, acting on any other vector is equal to, this is just a definition, x inner product with V divided by x with an inner product with itself. Okay, and similarly for bras. So V acted on by my projection operator is equal to V x inner product divided by x X inner product times the bra X. Okay, and that's supposed to be true for every vector V. That's the definition of this thing. So a good special case is, what if X has norm 1? So norm 1 means X inner product with itself is 1. And so then it was a waste of time to write all these denominators in that special case. And so you can just write that the projection operator P sub X is, I can write it like this way. Whoops, I don't know what that was. It was ket X bra X, right? And so that's our definition of the projection operator when it has norm 1. And so that tells us P sub X acting on any vector is X times X inner product V. So notice what happens is, this is right here, this is a complex number. So that's telling us when we project onto the vector X, we get something proportional to X. And how proportional is it? This is the constant of proportionality, X inner product with V. Okay, so we're out of time, but next time what we're going to do is actually relate these two examples. We're going to write the identity operator as a sum of projection operators. So next time, I equals sum of projection operators. Okay, so we've now covered everything in class that you need to do homework set 1, or almost everything. We didn't go over black body radiation. As you may notice, there are occasionally things I'm skipping in the notes. There are also things in the notes that I've skipped, but we will come back to. And that includes, we've skipped talking about the Dirac delta function, but I promise you that we will come back to that very soon. So the homework is due on Wednesday. I believe Monday is a holiday, is that right? Monday's Labor Day? So
No,
we
it's
won't
next
have,
Monday.
Monday.
So we won't have class
Not
Monday.
this Monday, but next Monday.
Wait, is it Monday there is class?
Yeah.
Oh, okay. All right, good. So in any case, the homework's due on Wednesday. And so if you have any questions, be sure to send me email or request a Zoom.
What time on Wednesday is it due?
So I'm not very picky. I forget what I said in the syllabus, but basically I never start grading the homework on the day that it's due anyway. So if you turn it in by midnight, I'm not going to complain.
Thank you.
Sure. Okay, and if you have a good excuse, just let me know. If you've got any sort of good excuse, I'll give you extra time within reason. All right, if there are no other questions, then I'll see you on Wednesday.
I have a slightly silly question about note-taking. When writing phi, you had mentioned I got the wrong phi down, or I mixed them up.
Oh,
Is that
yeah.
because we're going to introduce the other one later and I need to use the one you're using?
So I don't think I'm ever going to distinguish between them, just to write what we're talking about. There's that phi, and then there's this phi. To me, they're the same thing. That's probably sloppy on my part, but yeah. So I don't think I'm going to make a big deal about distinguishing the two. I just call them both phi. And then capital Phi looks like this. Okay?
Okay.
All right. Other questions? All right. If not, I will see you on Monday.
See you Monday. Have a good weekend, everyone.
Thank you.
Bye.
Bye.
Thank you. All right, see you. Thank you.